Okay, hi guys. Hope you're all doing well. So this is the first lesson that we're going to do with new material, and we're going to learn about the mole. Okay, so this is our first lesson in Unit 3, which is all about quantities in chemical reactions. All right, so I have a question. Have you been drinking water? I hope you have been. It's going to keep you healthy, it's going to keep you hydrated, but have you ever stopped and think about all the different molecules that you are drinking? Well, I can tell you, because of my knowledge of what I'm going to teach you in Unit 3, that if you have just one plain old cup of water, so 250 milliliters, you are actually you're drinking 8.35 times 10 to the 24 molecules of water. Okay? And if you want to think about it in terms of atoms, you're drinking 2.51 times 10 to the 25 atoms. These are astronomical numbers. These are numbers that we have a really hard time thinking about, even me trying to find out what the name of these numbers are on the internet. It was difficult, whether it's septillion, sextillion, heptillion, I don't know, right? So I'm just going to leave it in scientific notation. Do you see how these numbers are written? Scientific notation, these numbers here are always a number between 1 and 9.999 infinity, okay? So it's never 0 point something, and it's never 10 or 11. It's always in between 1 to 9.999, okay? And then the second part of this number are, they're telling me how many zeros are part of this number. Okay, so this is called scientific notation. It's very important to understand within this unit because we're going to be dealing with astronomical numbers. Just think about it. This is one glass of water, and there's 8.35 times 10 to the 24 molecules of water within it. I'm going to teach you, let's do a couple examples. Let's think about, I'm going to pick a number, let's say 1, 2, 3. Okay, let's pick a really, really big number here. Well, actually, that's not too big, 123,000. So I have to take a decimal. I have to make this number somewhere between 1 and 9.99, whatever. Okay, so there's this decimal here. I'm going to move it 1, 2, 3, 4, 5. I can move it 5 spaces. And you see that when I move it to this spot here, I go from it being 123,000, and each time we progressively move the decimal over, the number gets smaller and smaller. So say if I had the decimal here, this spot right here, it'd be 123. If I moved it over here, it'd be 12.3. But if I finally move it to this spot here, it's 1.23. And that's the number I want. It's between 1 and 9.999, whatever, okay? Now we have to, of course, 123,000 is not 1.23. So we need that times 10 to show me, to change 1.23 to being 123,000. Well, how many spaces did you move? You moved 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 different spaces. So the way that you count it is the decimal place starts here. So you move it 1, 2, 3, 4, 5. Okay, so because you're moving it to the left, because this is a number bigger than 0, 123,000, my exponent is going to be a positive number. Okay, so this is how I change 123,000 into scientific notation. 1.23 times 10 to the power of 5. Okay, let's try a different example. Let's try something really, really, really small. Okay, 0.00973. Okay, so the first step I have to do is I have to make it a number between 1 and 9.99. So if I move the decimal place 1 spot, 2 spot, 3 spot, do you see how now it is 9.73? And that's what I want. Now, of course, this number is not 9.73, so I have to think about how many spots I moved the decimal place. So I started here and I moved 1, 2, 3 spots. If I have a positive exponent though, that means that this number is bigger than 0. So since it's smaller than, sorry, not bigger than 0, bigger than 1, since this number is much smaller than 1, I have to make it a negative exponent, okay? So when the number is bigger than 1, in this case, you move the decimal to the left, you get a positive exponent. When you're moving the decimal to the right, and you have a number smaller than 1, you have a negative exponent. Okay, so that was important to teach you because now I get to teach you Avogadro's number and Avogadro's constant, which has to do with the mole. So I'm going to show you, or I'm going to ask you, when I say dozen, what comes to your mind? When I say pair, what comes to your mind? Well, when you think of a dozen, you might say a dozen eggs, a dozen donuts, but what you really are thinking about is a number, 12. It doesn't have to be a dozen eggs, it doesn't have to be a dozen donuts, but it does have to be 12 to be considered a dozen. 12 things. Just like a pair, you might think of a pair of shoes, a pair of socks, a dancing pair, a pair of dogs. What you're really thinking of is the number of 2, something coming in 2s. Again, it's 2 things. Why am I trying to get you to think about this? It's because when I say you have a mole of particles or a mole of atoms, a mole of molecules, a mole of dollars, a mole of things, what I'm really saying to you is that you have this gigantic number, 6.02 times 10 to the 23 things. So do you see how I use this arbitrary unit things? You can have a mole of dollars. Gosh, I wish. You could have a mole of birds, even better for me. You can have a mole of, in chemistry, atoms, molecules, ions, formula units. You can have all these different quantities within chemistry, which is why you have to read the question when you're given a stoichiometry question, or when you're given one of these questions that uses the mole. And when you read the question, it will say you have a mole of oxygen atoms, you have a mole of hydrogen molecules, you have a mole of hydrogen ions. The unit of the mole is completely dependent upon what you're talking about. To give you an example, I could say, oh, can you grab me a dozen? And you look at it, you'd say, Miss Villa, a dozen what? And I'd say, just grab me a dozen. A dozen what? I have to tell you what the dozen is. Can you grab me a dozen beakers? And now suddenly you know, hey, Miss Villa, she wants me to go to the cabinet and grab a dozen beakers. If you say to me, I have a mole, and you say, a mole of what? You say, a mole of water molecules. Okay, so do you see up here, I had two different quantities. Within water, I was talking about molecules of water, and I was talking about atoms. Because this water molecule is made up of 3 atoms. So using our knowledge of moles, we can determine the precise number of molecules, and I can convert it to number of atoms because I know the molecular formula of water. Okay, so that's well and dandy. Okay, so by the way, the mole was thought up by Avogadro. So this is known as Avogadro's constant. Okay, and because it's Avogadro's constant, we're going to make it symbol capital N with subscript A. And so whenever you see this, this is always 6.02 times 10 to the 23. Now instead of saying things, I'm going to say particles. Okay. So whenever I use this number, what I'm really finding out is this. Lowercase n. This is horrible. The unit, or sorry, the name of the unit is the mole, like the little creature. But when you see me writing it down beside a number, it's MOL. Like for instance, milliliter, you put ML. For mole, you put MOL. So you're using Avogadro's constant to calculate the number of moles from what? From this. When you see just capital N, then this is the number of particles. Okay, so Avogadro's constant always relies on this capital N because the number of particles, you can have atoms, okay? Atoms or ions. So for instance, if you're dealing with something like gold particles or silver particles or iron, I'm trying to think of things that come just by itself, right? You can also deal with ions, okay? Things that you aren't going to break up further. So I'm not going to break up a gold ion further. I'm not going to break up a silver ion further. I'm not going to break up any of those further. The second type are molecules. And so we use that name for atoms that are covalently bonded with each other. So let's look at water. I can calculate, so I could say to you, you have 23 molecules of water. Okay? Within one molecule of water, there's 3 atoms. Okay, so if I say you have 23 molecules, that's also, you can say 23 times 3 is 69. I have 23 molecules of water, or I have 69 atoms from the 23 molecules of water. Okay, so you're able to do these conversions. Something more complex, C6H12O6. What's another one? Carbon dioxide, methane. These are all compounds that have more than one atom. And so I can give you the number of molecules and you can break it up further and tell me how many hydrogen atoms are there, how many oxygen atoms are there, how many carbon atoms, etc., etc. And then the last one are my formula units. And I rather vulgarly short form it to FUs. Okay, so formula units. So if we have atoms and ions, if we have molecules, if we have formula units, these are going to be my ionic compounds. Okay, they come in crystal form. So I'm never just talking about, I'm not talking about one molecule of, say, copper 2 chloride or one molecule of aluminum hydroxide. I'm talking about formula units. And because they come in crystals and because you can't just isolate one water molecule, or you can't isolate an ionic compound the way that you can isolate molecules, this is why we use formula units instead. Okay, so let's look back. We have, from the question, you'll be given either the number of particles that you begin with or the number of moles. These are two quantities. They're measurable or that you can calculate them. And the way that you can convert them, the way that you can measure them, is by using this unit or this constant here, Avogadro's constant. So if you can calculate these things, that means there has to be a formula. And our formula is mole equals number of things, number of particles, divided by Avogadro's constant. So let's label them. These are my moles. This is my number of particles. And this is Avogadro's constant, which is always 6.02 times 10 to the 23. It's actually 6.02214. You can keep on going times 10 to the 23, but that's too much, okay? So I always just do 6.02 times 10 to the 23. This is our formula. So obviously, I said to you before, you're either calculating number of moles or number of particles. So if you were to rearrange the equation and you want to calculate number of particles, you're going to take the number of moles that you've been given and you're going to multiply it by Avogadro's constant. I'm going to ask you guys, I don't know when you'll use it, but get a piece of paper and make a formula sheet. I love formula sheets. I use them all the way up to university, and you might be saying, well, why am I making a formula sheet if I'm not using quiz, if I'm not going to do a quiz, if I'm not going to do a test, et cetera, et cetera. Or even if we were in school, I would say you aren't allowed to use your formula sheet on your quiz or your test. But the reason why is because having a formula sheet, it's going to make these formulas more available to you. So when you are calculating, you're going to have your formula sheet right there. You're going to see them. You're going to get to know your formula sheet. And then that's going to help you memorize these a lot easier. I'll be honest, in chemistry, the further you go, you won't use Avogadro's constant as much. You won't really talk about number of particles. However, as you begin this journey into understanding and discovering moles, this is the unit of chemistry. We don't really talk about grams when we're talking about chemical reactions, unless we're changing grams into moles, because mole is the quantity that actually lets us think about how many molecules, how many things. So formula units or molecules are actually being involved in the chemical reaction. Okay, so let's try a question. I'm going to give you a, whoops, let me start off. So you have 1.25 moles of water. Okay, so the first thing I'm going to ask you is, how many molecules do you have? And then the second thing I'll ask you is, how many atoms do you have? So let's look at this question. I'm going to ask you, take a second. I want you to think about what you're going to do, what strategy you're going to do, and what's your formula that you're going to use. So you have 1.245 moles of water. Which formula? Obviously, I've only given you one formula so far, but how are you going to arrange it? What are you going to put into it? So let's think about, I have this quantity here. What exactly is it? Is it little n? Is it big N? What is it? Well, you can see from here that anything that is mole is little n. So I have little n. Okay. And now you can also use the constant. Why? Because it never changes. Okay. Now I'm going to show you how you actually change the units of Avogadro's constant. I said to you before, they're flexible, and you have to read the question. Well, it's number things per mole, always. And when I read this, how many molecules do I have? Well, I have to read the question. You have 1.25 moles of water. Is water a molecule? Yes, it is. So if you have 1.25 moles of water, you're talking about molecules instantly. Okay. So what we're trying to calculate here is big N. And if you look up here, I'm going to use this formula. N equals small n times Avogadro's constant. And the reason why I'm writing out all these units is because if you cross this out and cross this out, you're left with molecules. Okay, so take a second, do that on your calculator. Try it out. And I get 7.53 times 10 to the 23 molecules of water. Now, how I usually will write this is I'll put little subscripts there. Okay, so how many atoms do you have? We have this information that we took from A. Okay. Look at the water molecule, H2O. There's 2 hydrogens, there's 1 oxygen. So we're going to do conversion. For every 1 molecule of water, you have 3 atoms. Students sometimes get stuck on this, but I want you to think about in your head. If you have $1, how many quarters do you have? 4. If you have $1, how many dimes do you have? 10. If you have $1, how many nickels do you have? 20. Think about the fact that you can have a large unit that is made up of smaller units. You just have to define it. If I said you have $1, which means you have 4. You say 4 what? You have to define it. You have 4 quarters. So when I'm looking at, I have 7.53 times 10 to the 23 molecules of water. If I want to look at, I want to find number of atoms. So you're going to use what I call like a multiplier or a conversion. You put what you want on the numerator and what you got on the denominator. So in question B, how many atoms do you have? What you want is atoms. And what you have, what you got, are molecules. So think about it. you have a molecule of water. How many atoms is it? Which one's going to have the coefficient 1? Which one's, you have to think of it intuitively. So if you have one molecule of water, it's made up of 3 atoms. And this is the conversion. So that when I have molecules here and molecules in the denominator, I'm crossing it out, and I'm left with this, atoms, which is exactly what the question is asking me for. So then I do number of atoms equals 7.53 times 10 to the 23 times 3. What's that going to be? Let's see. That's going to be 2.26 times 10 to the 24 atoms. Okay. So that's how you go from mole to number of molecules or number of atoms. Let's try the reverse. So number 2, you have 7.98 times 10 to the 25 atoms of gold. How many moles of gold do you have? Let's look at the question. We have this piece of information here, 7.98 times 10 to the 25 atoms. What is this? This is big N. That's the number of things, number of particles of gold. So it's big N. We have always Avogadro's constant. And so what we're trying to find is little n. And the way that you do it, our formula is number of particles divided by Avogadro's constant. So what's my unit for Avogadro's constant? Well, it's blank per mole. When we read this question, you have 7.98 times 10 to the 25 atoms of gold. So when I'm looking at Avogadro's constant here, I have atoms per mole that I'm calculating. It's not a molecule, it's not a formula unit, it's atoms per gold. Okay, so do it on your calculator. We have 7.98, and I get 1.33 times 10 to the 2 mole. So that's a huge number, but it's of gold. Everybody wants that. Okay, so you're just, if you're looking at how I'm writing my final answer, I'm putting, it's really ugly, small n to represent number of moles, subscript AU for gold, and I have 1.33 times 10 to the 2 moles, and actually I don't even have to write this, of gold. And then that's your final answer. Okay, so try some of the questions from the textbook and we'll see how that goes. Hope you guys are all well, and if you have any questions, please email me or respond on the Google Classroom or on the actual YouTube video so that I get a notification. All right, take care.